So last time we proved that by incidence matrices one can make explicit the cellular chain complex, and of course that's good for doing actual calculation. So that's why we thought we'd now present an example computation where one really makes the cellular chain complex of a relevant space explicit and computes the homology. And the space in question for this video will be the so-called length space. So to say what that is, let us first of all fix a positive integer m. So let m be a positive integer. And moreover, let's fix a family of other positive integers which are all supposed to be co-prime to m. So I'll call them L1 until Ln. Let those be co-prime to m. Then out of this data, I'm going to construct an action of the cyclic group Z mod mz on the 2n-1 dimensional sphere. So the group Z mod mz will act on the 2n-1 dimensional sphere, which as usual we view as the unit sphere and in the complex vector space C to the n. And the good thing about such a cyclic group is to describe the whole action of the group, it's enough if I tell you what the generator does. And it does the following. We just say this action is generated by call this map rho. So it takes now an element of this 2n-1 sphere. So that's an n-tuple of complex numbers. Let's get rid of the dot here. Z1 until Zn. And now we have these n different integers L1 to Ln, and I rotate each of these n coordinates by an angle of 2 pi divided by this Li, say, or Lj. So I multiply this one by e to the 2 pi I L1 over m. Sorry, I don't know if I said it correctly. I want to rotate by this fraction here of the full circle, the L1 over m fraction. And this we go through until Ln over m times Zn. Okay, so this clearly gives back an element of norm 1, and therefore it's a map from the circle into itself. And now the length space, the one we want to compute the homology of today, is just defined as the quotient space of this action. So that's the following definition. Let's call it L, or to remind ourselves of all the data that defines it, we put a lower index m here, and in parentheses we put those n numbers, Lm, L1 to Ln. And that is the 2n-1 sphere divided by this group action. So the space of orbits of this group action. And this one is called a length space. And let's just say of type, and we just repeat the defining data. So of type m, L1 until Ln. Okay, so one example might already be familiar to you. Namely, in case we consider m equals 2, then the condition that those numbers Li are supposed to be co-prime to 2 already fix what they should be, basically. They only matter up to mod m by definition here. So in that case, being co-prime just means they are 1. And then the corresponding space L2 of, well, let's just write ones here. That is the real projective space of dimension 2n-1, because in that case, Z mod 2 just acts by the antipodal action, and therefore we get this quotient space, which is the real projective space of dimension 2n-1. So in this sense, length spaces are generalizations of projective spaces. Next observation is that the action is actually free. So let's convince ourselves about that. So if I have some point in the sphere here, then its norm must be 1, so there must be some coordinate which is non-zero, and this coordinate is multiplied by e to the pi I L1 m, and then I do this rotation as many times as I apply an element of k in Z mod mz to it. But this can only be 1 if this k with which I multiply here is actually itself a multiple of m, because Li was chosen co-prime to m. So in other words, only the identity element of this group acts trivially. And all the other group elements move points. And this is what the action is free means. And this has the consequence that actually the quotient map from the space, so from the 2n-1 sphere to the orbit space, the length space, is a covering map. And since orbits have length m, because the group has m elements, it's an m-sheeted covering.
Yeah, another consequence of the freeness of the action is that L is a manifold.
A covering map is a local homeomorphism, and being a manifold is essentially a local condition. Yeah. So therefore, yes, you get a manifold again. Right, so these are odd-dimensional manifolds, and they're also of interest in topology, but we will just, before I illuminate what their origin is and why they were defined, let's first of all compute their homology. And we now learned that computing homology, well, we already have some tools. We know Meyer-Wieterer sequences and so forth. But our most recent tool is actually to find a CW structure on a space and then actually compute the cellular chain complex and compute the algebraic homology out of this chain complex. And this is the method we want to apply this time. So let's just say goal, or first goal is find a CW structure on the length space. Okay, so we do this step by step, and it actually requires some mental effort to do this. And the first thing we do is within this 2n-1 sphere, I find many embedded circles, of course, great circles, and we fix one, namely the one that only sits in the last coordinate. So consider the circle, call it C as in circle, consisting of all those points in C to the n whose first n-1 coordinates are 0. And the last coordinate then, to make it live on the sphere, must be of norm 1. So this is a circle which lies in this 2n-1 sphere. And we subdivide this circle just by the regular m-gon. So we say vertices of the subdivision of the circle are just the points e to the 2 pi ij over m. So which we subdivide by vertices e to the 2 pi I j over m, of course for j ranging between 1 and m. Within the other n-1 coordinates, yeah, there sits an embedded 2n-3 dimensional sphere. Yeah? All those points where now the last coordinate is 0 and the first n-1 coordinates are supposed to define a vector of norm 1. And what we do now is we join each of our vertices we've just chosen, these m vertices, with this 2n-3 dimensional sphere. And we do this along great arcs within this 2n-1 dimensional big sphere. So join the jth vertex by great arcs to the sphere of dimension 2n minus 3 that sits here in this subspace c to the n minus 1 times last coordinate is supposed to be set equal to 0. Well, first of all, if we want to join by great arcs, we should make sure that there are unique such choices, but for any 2 points on the sphere, there is a unique arc connecting them, unless those 2 points are conjugate, yeah, are antipodal points. But of course, the antipodal point of a point here is just the same point with a minus sign in front of it, and that does not lie in this 2n minus 3 dimensional sphere. So that never happens, and we have a unique great arc to all of those points in the 2n minus 3 sphere. And these we take all together to obtain what's geometrically now a 2n minus 2 dimensional disk. And therefore we also call it like this, 2n minus 2, and we've put the index j here corresponding to the vertex we started with. Now, why is that? Well, we have got 1 point, and we join it to every point of a 2n minus 3 dimensional sphere, and that's sort of the same thing as coning off a 2n minus 3 dimensional sphere. So you can just think of the vertex as being the midpoint of this new disk. Yeah? The only thing is that it's not flat in space, but it's, yeah, I mean, the radial directions are along great arcs. This is the thing you have to get used to. To obtain this disk with boundary sphere S2n minus 3. So d 2n minus 2j is just this one and the same sphere. Yeah. So these disks here are different, therefore they're indexed by j, but they have a common boundary, which is this one fixed 2n minus 3 sphere. Okay. And now we do the same thing, not only for the vertices in our fixed circle, but actually also for the points between those vertices. So we join the whole edge, yeah, sitting between 2 such vertices with this 2n minus 3 dimensional sphere. And then, of course, with what comes out has 1 dimension higher, we get something which is 2 minus 1 dimensional. Join the jth edge, instead of vertex now edge, the jth edge in this circle C, to the sphere S to the 2n minus 3, to obtain now a 2n minus 1 dimensional disk, 2n minus 1j, which is now bounded, well, by the 2 disks corresponding to the jth and the j plus first vertex. Yeah? So it's bounded by d to the 2n minus 2j and d to the 2n minus 2j plus 1. Okay? So
already forgot what C is. What is C?
C is the circle we started with, the circle lying in the last coordinate.
Ah, okay.
This circle...
And it had, yeah, okay, had these vertices and they partitioned it into edges. These are these edges.
Exactly.
Okay.
Yeah, we have the
and
circle.
Then I have to absorb this.
Yes, go ahead.
Join the edge to the same as 2n minus 3.
It's always the one and the same sphere, yes. So if you want, this edge is now a family of points. The initial point of this edge, the starting point, if you join this to the sphere, then you get 1 disk. Yeah? If you now vary the point on the edge towards the other vertex, then you vary through a family. You vary through a family of disks, which all have the same boundary sphere still. Yeah. So in other words, this whole family, if you vary through those disks, is now a disk of 1 dimension higher, and it's bounded by 2 curved disks from either side, corresponding to the 2 disks we chose before for the jth and j plus first vertex.
Right. It's like a solid cylinder between these.
Not quite. It's a solid cylinder, but the tubular surface of the cylinder is one and the same circle. So that's actually why this is already there. We already see the lens. Mm-hmm. Yeah.
Okay.
So I mean, here I will I will try to draw a picture later, but maybe one already sees this here. So this is our S2n minus 3, and I've sort of got the first disk is this round disk from the left-hand side corresponding to the jth vertex.
Yeah.
And corresponding to the j plus first vertex, we've got a round disk maybe bending towards the other side.
Yeah.
And if I walk along the edge from the jth vertex to the j plus first vertex, then in this disk I vary along disks from left to right. Yeah? So the bending will be less and less. In the middle I will have a straight disk, and then I bend towards the other part until I finally arrive at this one. Mm-hmm. So in this sense, okay, if I had drawn it a bit differently, it would already look like, if they weren't so much bent outside, it would already look like a lens. So this is the objects we will work with now. So now the next observation is, remember we have our map rho, which is the generating transformation of the 2n minus 1 sphere, generating the group action of Z mod mz on the sphere. And this has now the property that this fixed 2n minus 3 dimensional sphere in the first n minus 1 coordinates is an invariant subspace. This one's mapped to itself, which is completely clear, yeah, because this is the sphere where just the last coordinate is 0. So if we multiply now with our e to the 2 pi I something, then the last coordinate will still be 0, and the first ones will be somehow rotated, but it's still going to be a norm 1 element. So this is an invariant subset. And also for an element in the circle, we have the following formula. So rho of z is equal to e to the 2 pi I. And I think now I have a mistake in my notes, because this should be an n here, right? It's the last coordinate. Yes, I'm pretty sure. It should be like this, times z for z in the circle. Yeah, so if you're in the circle, that's an element where only the last coordinate is some norm 1 complex number, and that once by the action is multiplied by this number with ln here. So it's rotated just around the circle. And what this means now is actually that our group Z mod mz not only acts on this whole sphere, but it also permutes those disks which we have just constructed. Yeah? So conclusion is Z mod mz acts both on this family of 2n minus 2 dimensional disks, and it also acts on the family of bigger disks, d2n minus 1 j. Yeah, so in our picture, sort of the next lens, the next disk would now come here as a right neighbor, say, yeah, and the action would just be that it shifts the one lens to, it rotates it around the circle by this angle, what is it, 2 pi ln divided by m. Yeah, so it permutes this, these big disks, and it does so actually by a full m cycle. Yeah, because the rotation was so chosen that it really has order m here, because ln is co-prime to m, and therefore this action is just the permutation of this set of m elements, which is really a full m cycle. And the same thing applies then, of course, to the boundary disks of these bigger disks. Yeah, they are also like permuted by a full m cycle within this 2n minus 1 dimensional sphere. So this is an action by a full m cycle. So now one more remark is that right now this action is not necessarily in such a way that one disk is mapped to the adjacent one. Yeah, because this would be the case if the number ln was equal to 1, then this is what would happen. But since it's allowed to be any number co-prime to m, it will generally not be the case, but we can take some power such that this happens. So for some power it will be mapped to the neighboring disk. And we can just do it by solving the equation r times ln is supposed to be 1 mod m. So in other words, I just take as r the multiplicative inverse in z mod mz. And for this power, so if I apply my transformation r times, then I actually get to the neighboring disk. So then this one's mapped to the 2n minus 2 dimensional disk, now indexed by j plus 1. And the same goes for their boundary disks. Yeah? So rho to the r of d. These were the boundary disks. I put here a 2, so now it's also true for the big disk. 2n minus 1 gj is equal to d2n minus 1 j plus 1. And it's now more convenient to have this transformation as to map one disk to the neighboring one, because then we can now understand what the quotient is, just by using this identification. Namely, we now see that our length space, well, since this is just, the action is just a full cycle, permutes all those disks, so we can sort of take one of those disks as a representative and only have to make sure we understand how the boundaries, how the two boundary disks are glued together. And this is now simply done as follows. So I take my, my big disk. For some j, any j is fine. And I identify in this disk now boundary points on the two boundary disks. Namely, if I have a point here within the one boundary disk, let's say the one that bends left, 2n minus 2j, then I identify it by the point, and now I take the rth power of rho, apply this to this element z, and now I end up in the neighboring disk, and these 2 points I do identify. J plus 1. And I can do this for any j. You can do it for j equals 1 if you want, but it doesn't matter.
That's a creative notation for a Cauchy space.
Yeah, I didn't know how I wanted to write it.
Okay.
I mean, yeah, the equivalence relation is only points in these two boundary disks get identified. Yeah, all the other equivalence classes are single point elements, and these are identified in pairs by this. Relation. Yeah, so every point in the, say, left, let's be pictorial. Every point in the left boundary disk is identified with the point rho to the rz in the right boundary disk. Okay, and now let's try to draw a picture of what one cannot draw a picture of. So let's try to visualize the case n equals 2. So let me see if I get it right. It's typically drawn, so that you're not confused by the literature, not the way we did it up here, where it's sort of vertical, but it's usually drawn horizontally. So let me also do it like this. So now the two boundary disks bend north and south, and in the middle we have this equator 2n minus 3. Come on, yeah. Okay. So here is my 2n minus 3 sphere. On top, I've got my bent over disk d2n minus 2j. On the bottom, I've got my disk d2n minus 2j plus 1. And right. So now the identification of the two boundary disks is as follows. We take the upper disk, we reflect it along the plane in which this S2n minus 3 lies, so that's just this equator plane in the picture. And then we have to rotate it by the angle that's determined by this number L1 we chose in the beginning. So actually it's by the angle 2 pi times L1 times r divided by m. And then these points get identified with each other. So to make this rotation maybe clearer, let's divide this circle by this angle 2L 2 pi L1R divided by m. So I get, I don't know how much I will draw. Let's just go around the circle. 3, let's draw them bigger. 4, 5, 6, 7, say. And to see the action of how one rotates this, let's draw the axis here. And let's also draw sort of the trajectories which get mapped to one another. So if this is the North Pole and this is the South Pole, then this arc here from here to here is then mapped to this arc here, and this one to this arc, then to this arc, then to this arc here, to this arc, and here to this one. Okay, and the same thing on the other side. So we've got the South Pole somewhere here in the back, and this one gets like this one here, this one bends over here, and so on and so forth. So this should go to here, this should go to here, this should go to here. Whiteboard is not so responsive. Okay, like this. Can one still see something? I guess so,
yep.
Yeah? Okay, right. So this is sort of indicating the identification, yeah? So this is, let's draw what it is. So this is D3 now is the big one. So this is our lens, yeah? That's the whole thing, and it's bounded by D2J and D2J plus 1, which is the upper and lower hemisphere. So upper and lower curved boundary disk.
You're drawing the equivariant picture within S2n minus 1, right?
Yes, this is still in S2n minus 1.
And
yes.
In that case, for n equals 2, you think of it as the one-point compactification of R3. So that this line from the bottom to the top is actually a circle, right? Because they go to the points at infinity.
Yeah,
and close up
that's
there.
maybe a good way to think about it. Okay, so let's say the vertical line is a circle, and they join at the point in infinity, and then those lenses are at the jth edge. I mean, yeah, this infinite line is now intersected into jth parts. Yeah, it's the way you need to do it. Yeah, so you draw sort of 6, 7 points here, and then the final big part is also one edge. And what's bad about this imagination is that this one, which is bending down here, should also bend upwards to the next one. Yeah, I mean, this one is also bounding the lens which goes on top, and this one is also bounding the lens which goes on to the bottom here. Yeah, and so on and so forth. Yeah, that's right. Yes. And corresponding to such an edge, so say here was one point, one big point, here was another big point here. Now these disks are bent over, yeah? So this is a solid 3-ball, the 3-dimensional disk, and along these edges, all those disks have as a common boundary sphere this S2n minus 3, which is just an S1 here in the middle. Yeah. Yes. Exactly. And now I take one of those lenses as my representative of the quotient space, but then of course I have to identify the 2 boundary disks, and I have to do it by this transformation rho. And this transformation rho in this picture means I bend this down, so I reflect the upper hemisphere to the lower hemisphere, and then I still have to rotate by an angle of 2 pi L1 times r divided by m. And this is sort of what I wanted to illustrate in this picture with these additional lines here, because they say how much I twist, yeah? So this is sort of the picture one should think about here. So maybe to make it clearer, maybe let's say what two possible points are. So I don't know, say I've got this point here, which lies in the lower left corner of this section here. Then I first have to reflect it down, then it lies here, and then I have to rotate by the angle 2 pi L1 r divided by m, and then maybe that's in this case just going until here or something. Yeah, but where it ends up on what of these sections, that depends on the number L1 in this case. All right, so now from this, from these illustrations, we can now say what the CW structure of those quotient spaces are. Namely, first of all, we see this inductive character. So we have that the n minus first length space, if I only pick n minus 1 numbers, L1 to Ln minus 1, actually lies inside the next one, where I pick one number more, L1 to Ln. And the latter is being obtained from the former by attaching two cells, one of dimension 2n minus 2 and one of dimension 2n minus 1. Okay, so remember we had this disk 2n minus 3 equatorial disk here, and within sort of this, in the quotient space then, within this disk we find the previous length space of the first n minus 1 coordinates. And we have attached now one 2n minus 2 dimensional disk, which in this picture here still consists of two disks here, but remember they are identified in the quotient space. So there's just one 2n minus 2 dimensional cell attached to this boundary equator, and one big 2n minus first dimensional disk, which is just the interior of the interior points here in this picture. And since going up by one complex dimension means going up by two real dimensions, it says, or this practically says that we're just attaching one cell in each degree, in each real dimension. And therefore the cellular chain complex is very easy, consists of one Z summoned in each degree. Oops. So I think we call the cellular chain complex CCW star. So we'll now describe it. And remember, strictly speaking, we defined a cellular chain complex with respect to a given homology theory. But in this case, let's just say this homology theory is singular homology with coefficients in Z. So H star is just supposed to be H sing star with coefficients in Z. So how does it look like? Let's put the degree up here. And well, we have no cell in dimension 2n. We have one cell in dimension 2n minus 1. So there's one Z summoned here. Then one cell in dimension 2n minus 2. And so on and so forth. Always just one cell. So let's see how far we want to draw it. Maybe a tiny little more. Z 0. So this is 2n minus 2, this is 2n minus 3. This is 0, this is 1, this is 2.
So the Euler characteristic is 0.
Yeah. Is it an odd number or an even number?
It's an odd number.
Yeah.
And this is what we expected.
Yes.
since it's covered by S2n-1.
It's an odd number, but we start counting by 0. This is what I was confused about. So it's an even number of summands, and therefore the alternating sum is 0.
Right.
Yes, sorry. Yeah, right. The Euler characteristic is 0, because the Euler characteristic of all odd-dimensional manifolds is 0 for a reason which we don't know yet. But yeah. It's also, did you say that the Euler characteristic is multiplicative with respect to covering maps?
No.
Okay, so maybe that's another thing.
It's maybe an exercise.
Yeah. Yeah, right. So anyhow,
it's maybe not for the audience, but for us,
yes,
a good check that everything.
It should be right. Yes.
Should be right.
Okay, so these are the chain modules, and we still need to find the boundary maps here, and these were defined in terms of the attaching maps of the cell. And let's look at the attaching map of the 2n-1 dimensional cell. If we want to attach a 2n-1 dimensional cell, then we need to consider an attaching map on the boundary sphere, which is now 2n-2 dimensional. And so let's look at the picture again. So how is this 3-cell, in the picture it's a 3-cell, so in this case let's look at the 3-cell, the big cell. How is it attached? Well, it's attached, as you can see in the picture, there's the boundary 2n-2 sphere, that's this 2 sphere you see here at the surface of this disk here, and it's attached by the lower hemisphere, say in the usual way. Yeah, this is sort of the representative we're considering here. And now the upper hemisphere is identified with this lower representative, this lower hemisphere, by reflecting and rotating by this angle 2 pi L1R divided by m. So the rest, so sort of the 2n-3 skeleton, in which this sphere here lies, is collapsed to a point in this map defining the degree, so defining the incidence number. And therefore, I can say this map actually factors through a one-point union of two such spheres, which I obtain just by collapsing the equator of my 2n-2 dimensional sphere. Because that's all these points go to the collapsed points in the middle, in the 2n-3 dimensional sphere. And now, like I said, the lower disk, which now in this one-point union becomes a sphere again, is just mapped identically. But the second sphere here in the one-point union, which comes from the upper hemisphere, that's reflected down and afterwards rotated by a certain angle. So this is topologically a one-point union of the identity and a map of a rotation after a reflection. And this is all I need to know here, because it will only matter what this map induces on homology. And from there I go to the 2n-2 sphere, which I obtain by collapsing all but this one 2n-2 dimensional cell in the length space. So this is homomorphic to L2n-2. So this is the 2n-2 skeleton of our length space L, mod out, collapsing everything but this one cell. So Ln2 n-2 without this one 2n-2 dimensional cell. So actually, I think it was not good to call this the attaching map. It's the map which we called Fij last time. So the map coming from the attaching map, but afterwards you compose with this quotient map. So did we give it a name?
No, I don't think so.
Okay, so yeah, let's put. Let's call it the incidence map. I think that makes sense because it defines the incidence number. So it's the incidence map F of the 2n-1 dimensional cell and the only 2n-2 dimensional cell in the length space. So what does this map induce in 2n minus second reduced homology? Well, this reduced homology is additive with respect to coproducts. So I just get the sum of these two maps here. And h twiddle 2n minus 2 is a functor. So applying it to the identity just gives the identity. So the second map here is the composition of a reflection and afterwards a rotation. And we already know that a reflection induces in homology minus the identity. This was in one of the first videos. And the rotation actually is just homotopic to the identity map. So this does not change the outcome in homology. And therefore, this is actually not plus. It's identity minus the identity. There we go. And therefore, this is the zero map. And it induces, therefore, 0 as an incidence number. Yeah, so this shows the incidence matrix of degree 2n minus 1. It's just a 1 by 1 matrix, and it has only one entry, 0. Okay. So yeah, let's put this in the chain complex. So this first one here is just the 0 map. And now the second one. So let's call this the incidence map. Yeah, corresponding to the attached 2n minus 2-dimensional cell. So this is actually almost a bit easier to understand. Namely, the first one is just the covering projection going to the lens space. So that's Lm now, well, in this case to the earlier lens space, so the one with n minus 1 integers, which is just the 2n minus 3 skeleton of our lens space. And now, incidence map, I need to collapse the complement of the only open 2n minus 3-dimensional cell. So I take here L2n minus 3, mod out L2n minus 3 without this one cell. And again, this is now homeomorphic to S2n minus 3. Okay, so in this picture, the incidence map of the smaller dimensional sphere, that's the one where I walk along this equator. But in the quotient space, the new smaller dimensional cell is just one section of this equator. So if I walk around this equator, I walk m times through this cell here, and therefore my map down here factorizes actually through a one-point union of m different 2n minus 3-dimensional spheres. Whoops. And in all of these spheres are simply mapped onto the cell here by a degree 1 map, and therefore the full composition just has degree m. And actually, I can't decide yet whether it's plus or minus m here, the degree, but this also depends on the homeomorphism I have chosen here, yeah? Because I can take a degree minus 1 homeomorphism and change my push-out map here, and then I would get the other sign. So actually, while it does not matter if it's plus or minus m for the homology calculation, I can just say it's going to be plus m. So this is equal to m times the identity. And therefore, the incidence matrix 2n minus 3 is just m. Okay, so now we collected all we need here for the chain complex. The next term is multiplication by m, and then inductively it just alternates between zeros and m, so the next term is 0 again, and finally here it ends at 0, and here we've got an m. And now we see that there are 3 different cases for the homology now. So the kth reduced homology of the lens space, Lm L1 until Ln. That's Z in the beginning, k equals 0, and in the end, 2n minus 1. So let's see this. In the beginning, the last arrow is of course 0, so the kernel is everything, modulo the image, which is 0, that's nothing, so it gives a Z here. And very similarly here, this map is the 0 map, so the kernel is everything, nothing is mapped out. And then there's just two more cases. In case we're, when k is odd, then we are at, for example, at this Z here, then the kernel is everything, and mod out is the image of the multiplication by m, so this gives Z mod mz. And if k is even here in the in-between case, then actually multiplication by m is an injective map, and therefore the kernel is already 0, and so is the homology. So that gives the two remaining cases. It's Z mod mz if k lies between 0 and 2n minus 1, and in addition is odd. And finally, in all remaining cases, the homology is 0.
So the work for the very first differential one could spare, because if you know that the second differential is multiplication with m, then the first one has to be 0, because multiplication with m is injective, and composing two differentials must be 0. So that's the only way it could be. But it's better to see it. And it's geometrically why it is 0.
And does this work everywhere or only in the beginning? Does it? I mean, can I afterwards say it's alternatingly 0 and m?
I think so.
Yeah. Okay. Okay. Yeah. So this is the homology computation of the length spaces, but they were not defined just for fun, because they were defined because they have interesting properties. And actually, maybe the first thing that one might notice here is that in the homology you see the integer m, which is part of the data defining it, but you see neither of all those other integers here. Yeah? So one could wonder, does the space or the homotopy type of the space actually depend on the other integers, even though the homology doesn't see it? And that's actually true. So it does depend on those integers. Namely, the example is that the space L5, 1, 1 is not homotopy equivalent to the space L5, 1, 2. Yeah, so the m is the 5, therefore they have the same homology, but they're not homotopy equivalent if one chooses the numbers L1 and L2 in this fashion. And even worse than that, it can happen that two such length spaces are homotopy equivalent, namely, for example, L7, 1, 1 is homotopy equivalent to L7, 1, 2, but those two length spaces are not homeomorphic. So L7, 1, 1, oh yeah, let's just write it here. They're not homeomorphic. Yeah, and actually, if you think about it, it's not so clear that to come up with something like that. Yeah, two manifolds which are homotopy equivalent, not homeomorphic. For example, in dimension 2, that doesn't happen. Yeah, among surfaces, you find no such thing. So these were the first examples where this happens in dimension 3. And there is, okay, so maybe as another remark, you also do not see the other integers in the other homotopy invariants we know. Yeah, so the fundamental group of the length space is just Z mod mz, yeah, because the universal covering is S3, and we mod out this action by Z mod mz. So therefore, the fundamental group is Z mod mz. That one does not see the other integers either. And even the higher homotopy groups, which we just mentioned in this course, they are the same as the ones of the 2n minus 1 dimensional sphere. So they also do not depend on the integers L1 to Ln. So all the elementary algebraic topology does not see those integers, and yet again you have those strange occurrences here, and actually one has to come up with quite sophisticated invariants to see that such spaces are not homeomorphic. That leads to the so-called Reidemeister-Franz torsion, which was invented in the 30s to distinguish those spaces. Okay, and final thing, why length spaces are also important. I don't know what's going on here with the whiteboard.
You've written too much.
I what?
You've written too much.
Yes, maybe.
Cannot cope with that amount of mathematics.
I mean, neither can I, yeah. But this last remark, I hope it still allows me to write down. I can also consider an infinite length space, yeah? I mean, we just saw that those length spaces are contained one in the other, so I can just form an infinite length space as the co-limit of all those, along all those inclusions. Yeah, so and then by construction, sort of by definition, this defines a CW complex again, which is now infinite, yeah, because it carries the co-limit topology. And the strange thing is, despite that the homotopy type of those and homomorphism type of those finite length spaces does depend on the integers, this one doesn't anymore. So this one is independent of any sequence of integers co-prime to m that one might take here. So it's independent of L1, L2, and so forth, co-prime to m. And the reason, from a homotopy theoretical viewpoint, is that actually if one computes the universal covering of this infinite length space, then this is the infinite sphere. Yeah, just the co-limit of these 2n-1 spheres. And this, I think, we actually already gave in some exercise, or as an exercise, is a contractible space. So the infinite dimensional sphere is contractible. And spaces with contractible universal covering are called spherical, and they have this property that the homotopy type is actually already determined by the fundamental group. And yeah, therefore
which is the cyclic group of order m.
So they only depend on m for every m. Therefore, I don't have anything else here in the in the notation. For every m, we obtain such an infinite length space unique up to homotopy equivalence. And this is relevant for more advanced topics. Yeah, so actually, the homology of this space would be the group homology of this cyclic group Z mod mz. So in this sense, you will maybe encounter this object again later in your life.